Right. So I'm going to be talking to you today about structure-function relationships in sodium-ion batteries, and I shall move on. Okay, so introduction. There is significant potential in Indonesia to power Indonesian needs using photovoltaic power. If you look at the island of Java, for example, you're in the high area of the of this map. You can see here that there's a very high level of solar radiation, to the point where there is 14 times more solar radiation available than the country's current electricity consumption. And Indonesia has 40% of the world's geothermal energy store. So there is significant potential to get essentially free electricity from the sun and from geothermal once the capital is money has been spent on building the power infrastructure. But this is a plot of electricity usage in Indonesia, okay? And you can see here that it's flat throughout most of the day, and then there's a peak at around 8 p.m. in the evening, which then falls off as you go further into the night. This peak is associated when people get home from work. So the reason is that the workplace's electricity usage is probably similar throughout the day. Offices leave lights on, they leave air conditioning on. And actually, it's when people get home, they start to cook, they turn on their air conditioning, that you get this peak at 8 p.m. So you can see here that the peak in photovoltaic has got to be around lunchtime, because that's when the sun is the highest, when it's the most intense. It's also the load is around 8 p.m. in the evening. And that is mostly as a result of this problem here. This is a picture of a building somewhere in Jakarta. And you can see people have put air conditioning units on the outside of it. People get home, they switch on their air conditioning. Okay. So we need a way of storing this energy that we can make with photovoltaic cells to get into the peak usage. Okay. So the idea is that you have some kind of energy storage facility, whatever that might be. Okay. And you have a power plant, whatever that might be. And then you store the energy in this storage facility when not using it, such that it can be returned to the grid to run the houses and the factories in the evening when you are using it. So this power plant would be solar generation or other renewables as needed. And then this energy storage facility could be many sorts of different things. And here are some examples of the many sorts of different things the energy storage facility could be. So you have a pumped hydro system. This is in addition to all of these numbers here, which of course matter, right? There are some additional comments here. For example, pumped hydro is large scale. You need to have a big dam, basically. You need to pump it up high, which means that it's not suitable for all geographies. I'm not sure where you put one in Jakarta. It's not responsive to the short-term needs of the grid. It takes a long time to get the energy flowing. It's not suitable for microgrids because it's so large scale, and quite a large damage to the environment as a result of the fact that you need to dam a river or dam an area and then pump the water. And it's not suitable for it's got quite a low energy density, which of course is a problem. You want to have a high energy density, so it has a lower impact. Then you have compressed air with similar problems. This idea here is that you pump air into gas fields that used to have you get gas from that you've burned, or oil fields that you've made petrol from. Again, it's large scale and not suitable for all geographies. It would be situated quite a long way away from where the people are, because you don't tend to have gas fields or oil fields near them. It's not responsive, it's short term. Molten salt, you basically melt salt as a thermal store, is very slow and large scale and very expensive. Lithium-ion batteries are pretty expensive and have quite a low cycle lifetime. 1,000 cycles, which is the sort of lower end of this, is 3 years. If you think about it, your mobile phone will last 3 to 5 years before it needs a new battery. And it will be the same for energy storage, for static energy storage. Okay. Lead acid batteries, toxic with low lifetimes potentially, or also potentially high lifetimes, depending on what technology you use. With low energy density compared to other batteries. Now, flow batteries, which is an emerging technology. Hydrogen, well, hydrogen is often sourced from methane fields, which then produce CO2. Okay, so that isn't necessarily good for the environment. Okay, and then you have flywheels, which are not long-term storage. So these are all current technologies that none of them really suit what we need, to be honest. The most likely at the moment to work is lithium-ion batteries, just because we have the production. We have a high production. Despite the costs, we're making a lot of them because of cars. Now, cars. This is my car, used to be my car. In order for me to drive 800 kilometers, I would need 45 kilograms of diesel and a 2-kilogram fuel tank. It only takes me 5 minutes to refuel. This is the most popular car in my country that uses battery electric. In order to drive 160 kilometers, which is the maximum range of this car, I need to have 192 cells that are roughly 1 kilogram each. So that's 190 kilograms of battery. And its fast charging is 40 minutes rather than 5 minutes to refuel. Much lower range, much heavier battery. And actually, to drive this 800 kilometers, assuming I can fast charge, it'll take me 3.5 hours of charging. Realistically, I can't fast charge for 4 times in a row, otherwise I'm going to kill my battery. And so actually, it's going to take many more hours of charging, probably 20 hours of charging. Okay. Korean cars are not better than Japanese cars, but that's a subject to another talk. My point being that we need better batteries, even with transport. We need better batteries for static storage. We need better batteries for transport. Back to this point here, load photovoltaic cells. If you have electric cars, you're only ever going to increase this load peak because people get home from work, they plug in their car to charge overnight so that it's fully charged by the next day. This is complex. It might mean that we need swappable mopeds. We'll see. But this is complex. Now, why sodium batteries and electrodes from biomass? I've given you an introduction to batteries in my view. So there's a little bit more detail on lithium-ion batteries. Remember I said that they were quite expensive. Well, the energy used for battery manufacturing is, according to a source that I found on the internet, 500 megajoules per kilowatt hour battery, which is a lot of energy. That releases 200 kilograms of CO2 per kilowatt hour. Okay. The lithium is extracted from a limited number of countries, mainly in South America. Cobalt shortage is of a natural resource, actually with a limited number of countries also in South America, which is extracted from rock, which is environmentally damaging. Copper is used as a current collector, and that has high energy demands to extract. And graphite comes from mines, and this synthetic graphite from petroleum coal. This is a coal mine, or what do you do with the coal that's low grade? You burn it for electricity or making steel. That's bad for the environment, but you wouldn't throw that product away. If you're going to mine graphite from a high quality graphite from a mine, at the same time, you're going to take up the low quality coal to then sell as well. Petroleum coke, again, is the end of the line when it comes to petroleum refinery. So you have all of the petrochemicals that you make from taking crude oil up, and then you make coke from the stuff you can't use for anything else to turn into graphite. It's bad for the environment. So what about sodium-ion batteries? Well, firstly, sodium ions are everywhere and easy to extract. They're in the oceans that surround your wonderful nation. They're also more likely to come from sodium carbonate, which is everywhere. You don't necessarily need cobalt. You can use other materials for the electrodes. You don't need, in fact, you shouldn't use copper because copper reacts with sodium. Sodium degrades it. You need to use aluminium instead, which is much lower energy and easily recyclable. And then graphite, well, instead you can use biomass to make electrodes. So as a result, sodium-ion energy systems have got the potential to seriously decrease the cost of energy storage. Okay. Well, how does a battery work? The obvious way is that you have an anode, which is a carbon system. You have a cathode, which is not. There are quite a large number of different non-carbon cathodes. And then you charge by moving sodium ions from the cathode to the anode to store in the anode. And you discharge by moving them from the anode to the cathode. That's a fundamental principle of a sodium ion battery. You have an aluminium current connector on both sides. Here are a huge array of different materials that are used with cathodes for sodium ion batteries. And the non-graphitic carbon are the ones that I have been working on because they have a low working potential on this side and a high-ish capacity. Okay. And then cathodes are quite complex, a large number of different cathodes. In terms of electrolytes, here are a number of papers as a function of different sorts of electrolytes and a function of different sorts of binders. There's a particular spike in sodium chlorate and PBDF when it comes to electrolytes and binders. Just to summarize those two graphs slightly better, you can see down here for anode material, you're looking at carbon sulfoids and alloys of tin and antimony. And then up here, there are lots of different ideas for cathodes, such as sodium iron phosphates here, Prussian blues here, etc. And you can see there's quite a large number of different ideas. You also note that I don't see any, there's a cobalt compound here. So they do exist. But there are other options, and there are many other options. Okay, so how do you turn biowaste into carbons? Well, you take a biomass waste product, you put it into a pressure generator at 200 to 300 degrees C, and you cook it for a few hours at that temperature. Okay, if you harvest early, then you end up with chemicals that you can then refine and use for other materials, for other things. Okay, so these are bulk chemicals that you can then convert into reagents for other things. You can also harvest at the end, and then you end up with carbon dots, which can be used as fluorescent nanomaterials and photocatalysis and things like that. And here are some pictures of different fluorescences depending on the size of the dots, depending on the conditions in here. Or you can pyrolyze them at greater than 1,000 degrees C and end up with a whole host of different structures, which then can be used as electrocatalysis or gas absorption, supercaps, batteries. Okay, my techniques are that I take these compounds, put them into a beam of neutrons or X-rays, and I measure scattering in order to extract the pore size as a function of condition. So I can get information about the macropores, I can get information about the nanopores, and I can get information about the atomic structure. Okay, here is an example hydrothermal carbonization. It's a bit of a mixture, as you can see, but you can see fluorescent-like nanodots in one case, or in this case, the microdots. And in other cases, you can see a very porous structure. As you increase the temperature from annealing temperature, pyrolysis temperature, from 1,000 degrees C to 1,900 degrees C, you can see a graphite peak appearing on the Raman spectroscopy. So as you increase the temperature, you increase the order, okay? So the mechanism of storage in sodium-ion batteries is still under debate. It is believed that this region here, this plateau region here, corresponds to sodium that's sitting in the pores in here. Okay, and then this is intercalation between these expanded graphene layers, okay, in these pores. And then in this region here, where you see the slope, it is believed that it sits within nearly parallel graphene layers, okay, or binding at vacancies. Okay, that's what's believed. If you get different structures, and you may get different assignments in here, and this is a good example of the changing in the CV curve as a function of different structures that you might have in as you increase the annealing temperature. So let's go back to this structural characterization. How does this work? So we take biomass, we put it into a pressure vessel, we cook it in a hydrothermal pressure vessel for a few hours at 200 degrees C, and then we take it out and we anneal it. Okay, then we put it into an X-ray scattering machine, small angle X-ray scattering machine, which you get some peaks. These peaks correspond to structures in the material. So here we can tell pore size distribution. Here we can tell crystal structure. You can also do that with neutrons, where you might note that the Q range is a little bit different. You can get down to a lower Q range here with, well, this is D of A. So this is inverse angstroms. This is angstroms, I'm sorry. So this is essentially a Fourier transform of this. Okay, so you can measure with, at least with neutrons, down to an angstrom or so, up to tens of nanometers. With X-rays, you can get out to much lower Q, which is much higher. So in other words, you can get out to microns. Okay, so here are some results. So let's start by looking here. We normalize to the first peak. Okay, and then you can immediately see, as you increase the temperature from the precursor through to 1900 degrees C, as you increase that, you can see that the peaks sharpen. This is normalized here, so this is a real amplitude change. The peaks sharpen. That means we get more ordered. This region here is the extended graphite structure. This region down here is within the ring. Okay, we can define a couple of bonds here, right? D1 corresponds to a direct CC bond distance. D2 corresponds to the next nearest neighbor CCC distance. So that's 3 carbons. Okay. D3 corresponds to the carbon ring diameter. This little shoulder there, right? If we plot ratios of amplitudes, you can see amplitudes are changing here. If we plot ratio of amplitudes from as a function of temperature, you can immediately see that this one here, which is D2 over D1, so CCC over CC, okay, is increasing as you increase the temperature. In other words, there are more next nearest neighbors in the carbon treated at higher temperatures. So when we say this is CC bond, there isn't very much difference between a CH bond and a CO bond, actually. There isn't very much difference between them. However, you do end at CH and CO and CC will have a very similar distance, a very similar bond length. So actually, this is probably due to the increase in aromatic carbon at the expense of carbon hydrogen and carbon oxygen bonds. Okay. Now, if we look at the ratio of D3 to D1, we see a similar story where it increases as we increase the annealing temperature. And this is a result of more aromatic rings in the system. In other words, we have a larger number of carbon ring diameters in there. Then if you look at the higher Q stuff, where you're looking at nanopores, you can see there's also something going on here. Okay, so this is between black and green. You can see here that it becomes sharper. And then between green and purple, it becomes sharper still. But the actual position of the pore size distribution doesn't really change very much. It's just the sharpness that changes. Okay, that does suggest that it's the order that changes rather than the actual structure, but nonetheless. Now, if we look at pore diameter as a function of temperature, we fit this data. Apologies, I said that wrong. There is a pore size change, although you can't see it on the data. If you go with pore diameter as a function of temperature, you can see now that as you increase the temperature, pore diameter increases to 5 nanometers. Okay. And at the same time, the distance between the graphene sheets in the material moves from a high value to a value that is found in graphite. Okay, and it's the same here with a D2O20. This is D002. This is D020. And you can see it moves up towards the graphite value as you increase the temperature. So what's happening is we have a pore size increase and a slow increase in crystallinity as we increase the temperature. Okay. Now, what we find is that the minimum binding energy for these systems is around about 4 angstroms into layer distance. Okay, so D002, the minimum binding energy is 4 angstroms. 4 angstroms. So actually, we want lower temperature. We want lower temperature D002 in order to get a lower binding energy. We want a lower binding energy because that means that we can get the sodium in and out easily. It doesn't get stuck. But when you move to graphite, which is 3, suddenly the binding energy shoots up to a very high level. And even though we might be able to get sodium in, it makes it very hard to get sodium out again. Okay. And this is sort of borne up in the capacity measurements here. You can see here that there's a peak capacity at 1300 degrees C, which is still up at close to 4. So the idea here is that we're increasing crystallinity, which we need in order to get sodium in and out, but there comes a limit where it can get stuck, so we get it in, but we can't get it out. Okay, so the highest capacity here corresponds to the optimum position of the pore size and the O2 distance and the O2O distance. You need to get all of these optimized, which you can do with temperature. So GC 1300 appears to be the most appropriate annealing temperature. All right, just quickly, because I'm running out of time. We did some MUSR. Now, what MUSR does, I'm not going to go into the detail, is if you reduce you can see here between 50 Kelvin and 500 Kelvin, there is a significant change in this signal. The amplitude of this signal gives you the diffusion rate. Okay, so, or rather actually the relaxation, they start off at the same, and as time goes on, this relaxes. So this relaxation rate gives you the diffusion rate. Okay, essentially the faster the material, the ions diffuse, the lower coupling that it has on the probe, which means the lower the relaxation rate. So the bigger the amplitude at higher times. And as you can see here, we've plotted diffusion as a function of temperature. And we can see that for a fully sodiated sample, we have an activation energy of about 88 millielectron volts, 90 millielectron volts. And for a fully desodiated sample, where there is still sodium, because it gets stuck, we have a much higher activation energy of 152 millielectron volts. Okay, if we look at sodiated, the DFT graph says it should be roughly 100 millielectron volt activation energy, but we see 88, which is pretty good. This suggests that muons that sodium is migrating along the graphene sheet. For desodiated, the DFT calculations of the energy barriers are about 180 millielectron volts, while we see 150, so it's also of the right ballpark. And the DFT suggests that actually what's happening is that pathway 2 is happening here for the fully desodiated. So long distance migration is blocked. It can't escape 2 sheets for some of the sodium. In other words, the sodium, when it's desodiated, long migration is blocked. Okay. In other words, we have a low mobility site and we have a high mobility site. And that explains why we get capacity loss in these materials. Okay, so I'm going to skip this because I'm running out of time. I would just, let's do a summary. I'd just like to summarize that the waste biomass can be used to create carbon electrodes for sodium-ion batteries, that we're still at a relatively early stage, but the specific capacity of sodium-ion batteries of the order of 260 milliamp hours per gram is similar to lithium-ion batteries, which is of the order of 300 milliamp hours per gram, which is great news. The major problem with sodium-ion batteries is capacity loss after the first charge, and we have discovered that the sodium is stuck probably between graphene sheets. There's a lot to do with in situ and operando work, such as measuring where the sodium goes and controlling the hydrothermal process and pyrolysis. And we also need to use real biomass. Here is a team of people that have been working on this over the last few years. And then here's my contact details. And for those of you that haven't already been told this, we are running a climate change workshop in a few weeks. There still is time to register. I strongly encourage that you do. There is money available for a travel grant for people who give talks to travel and give the same talk at a conference of their choice, assuming that a travel grant that we are able to travel in a few months' time. So please consider this is an opportunity to bid for a travel grant to present your research at an international conference. We have lots of money to give away to people, and I hope that we'll have a very high turnout. Please go to this website to register and upload an abstract. Thank you very much, and it's a pleasure talking to you this morning, or this afternoon in your case.